set of matrices, H inverse H, H inverse, well, without loss of generality, I could put 1 in here and minus 1 in here. H. And you see that's a copy of the Grassmannian of n planes in 2n dimensional space. Why is that? Well, you see, this is equal to SU to n divided by S of UN times UN, because this is clearly a homogeneous space for SU2n. There's a transitive action on it by SU2n, by definition. And then what is the stabilizer? Well, the things that commute with this will be S of UN times UN, and that's the Grassmannian of n planes in C2n. Okay, so there's this manifold. So this minimal action, these minimal action stationary states, this is a whole manifold, some Grassmannian. And then up here there's another manifold, and another manifold, and another manifold. And now you could ask, what are the independent ways that you could flow downwards? Most of the time when you vary a path, the action will increase, but there's a finite dimensional space. It's like the renormalization group with a finite number of critical points, a finite number of relevant operators. There's a finite number of relevant, if you like, deformations that take you down. And the number of unstable nodes at higher critical loci is greater than or equal to 2n plus 2. For proof of that, see this beautiful book by John Milner called Morse Theory, which is one of the main sources for this lecture. And now what one does is one invokes Morse theory to say, well, oh ho, therefore this path space has the same homotopy type as this Grassmannian, at least for homotopy groups, up to this index here. Okay? So that means, you see, that pi j of the loop space of u, un, u2n, su2n, excuse me, is equal to pi j of the Grassmannian and n for j less than 2n plus 2. Okay. On the other hand, this is equal to pi j plus 1 of su2n. So here we had the pi j of the Grassmannian is pi j minus 1 of u. Here we have the pi j of the Grassmannian and pi j plus 1 of u. And so therefore we get periodicity. That's what we did last time. Are there any questions about that? Okay, so I'm going to continue on this theme today. And the first thing I want to do is I want to explain to you a little bit about Morse theory, so you have some intuition for why these statements are true. Okay. Now, I won't be able to prove everything that we need in the application of Morse theory here, but I hope I show you enough so that you find what I'm saying plausible. Okay, so just a brief digression on Morse theory. And CW complexes. And then after that digression, I'm going to go back and I'm going to talk a little bit about what happens when we try and do this for the real case. Okay. So you see the periodicity is now mod 8 instead of mod 2. So it's clearly, this discussion has to be a lot more elaborate. And I'll talk about that, and then I'll talk about the relation to Clifford algebras. Okay, so Morse theory. So the first thing we're going to do is we're going to make life simple by thinking about a finite dimensional manifold X. And so the idea of Morse theory is that the topology of X controls the critical behavior of any function h from x to r, and conversely, knowing the critical behavior of a function on x, you can learn about the topology of x. That's the line of reasoning we're using in this application. So let's recall that a P is a critical point if the derivative of h is 0 at P. And at a critical point, we choose some coordinate system, and we can form the Hessian, which is the matrix of second derivatives. And at a critical point, well, so that's some quadratic form. Now, it depends on the coordinate system you chose. However, if you make a change of coordinates, then h goes to some j, h, j transpose under change of coordinates, where j is the Jacobian of the coordinate transformation. I'm using the fact that it's a critical point to say that. And so things like the signature of h are well defined. So we can say that P is non-degenerate if h of little hp is a non-degenerate quadratic form. Now, a Morse function is a function h such that all critical points are non-degenerate. Now, in our application, we actually had a degenerate Morse function, because, after all, there was a whole manifold of solutions of minima. So there had to be some zero modes. So there was a finite dimensional space of zero modes. But that's okay. The main point there is that you're in this infinite dimensional space, and it was a finite dimensional space of zero modes. You can handle that. You work orthogonal to that space, and the rest is non-degenerate. So there's certainly an extension of Morse theory to something what's called degenerate Morse theory. But again, I'm simply taking the simplest possible case, because this is just a little digression. It's long enough as it is. Okay. So now we arrange the critical values in increasing order. C0 less than C1 less than C2. And then the idea is that we're going to build up, and I'm going to make that precise, the manifold X from the level sets. Or more precisely, let's let x sub a be the set of points in x such that h of x is less than or equal to a. Now, I should have said here that at a critical point, p, we let lambda p be the number of independent negative modes of our Hessian. And this is called the Morse index. So, in the language of physics, you might call it the number of unstable modes, number of independent unstable directions. Okay, so everybody's favorite example is to take a torus and put it on a table, and then let h be the height function. So you see there are then four critical points. P1 here, P2 here, P3 here, and P4 here. And the Morse indices here are 0, 1, 1, and 2. Up here, there are two independent directions that we can go down. Here, there's one direction going down and one direction going up. And similarly, P2 is also a saddle point. Okay, and so our XA might look like this. Or, sorry, and it will be everything below. Okay.
Can you always arrange them? I mean, can they be like bigger or equal to this C0, C1, C2? I mean, can you calculate them with the same value?
Yeah, that's a good question. Well, you can always arrange the critical values this way, but I think what you're saying, and this is true, is that you could have more than one critical point with the same critical value.
Oh.
Okay, now a small perturbation of the function will, okay, so if I had something like this, if I had a sphere, okay, I could have a critical height function like that, but now you see if I tip the table just a little bit, then by a small perturbation, I can make the values different. Yeah.
Is there any relation on the total sum of the Morse indexes? Like,
Yeah,
they should be 0, right? For if the manifold is compact.
No, they're not 0.
Oh.
Okay, so I wasn't planning to talk about that, but let me answer the question. So, it's not what I wanted to emphasize, but it's actually a very important part of Morse theory, so let me tell you about that. So what you can do is you can always form what's called the Morse polynomial. Okay. And one of the things that Morse was quite proud of was that this is a polynomial in T, and this is greater than or equal to, let's call this P sub m for Morse, and this P sub P of x and t, which is the sum over the Betti numbers of t to the k. Okay, so this polynomial always bounds this polynomial. In fact, the Morse polynomial is of x and t is equal to 1 plus t. Excuse me. The Morse polynomial minus the Poincaré polynomial is 1 plus t times q of t, where this is a polynomial with positive coefficients. And that implies what are called the Morse inequalities. In fact, it's a refinement of the Morse inequalities. And notice that it has the nice consequence that if you put t equals minus 1, then you get the Euler character.
Excuse me, so this Q of T doesn't depend on x?
No, this q will depend on x, and this q will depend on h. Yeah, so often in discussions of Morse theory, people really focus on this aspect of the theory. I'll say a few words about the supersymmetric quantum mechanics interpretation of Morse theory here. And if you read Witten's paper, you'll find that this is the aspect of Morse theory that he's really concentrating on. But it's not quite the aspect of Morse theory that we need here. Okay, now, a key lemma here is called the Morse lemma, is that if P is a non-degenerate critical point of H, then there exist coordinates in some neighborhood of H so that H looks like H of P minus x1 squared minus dot 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 minus x lambda squared plus x lambda plus 1 squared plus dot 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 plus x n squared if capital X is little n dimensional. And to prove this, you see, H minus H of P, let's call that F, vanishes at x equals 0. So we can write because we have a critical, we can write this, and then because P is a critical point, the GI's also vanished. So then this is xi xj times some g tilde ij at x. And moreover, because it's a non-degenerate critical point, the g tilde ij of 0 is a non-degenerate form. So we can diagonalize that, and then if g is real analytic, we can redefine our x's so that our function just looks like that. Okay. Now, there are two main theorems here, Theorem A and Theorem B. And Theorem A says that if the interval AB does not contain a critical value, then XA is diffeomorphic to XB. Okay. So, in my picture here, if I have A and I have some B like this, so then XB would be the blue region. then XA and XB are supposed to be diffeomorphic. And the idea, I'll just draw a picture. The idea is that, okay, so we have XB, we have XA, but we also have the gradient, nabla H. So that's defining some nice vector field on my manifold, and that vector field has no zeros anywhere in the relevant region here between XB and XA. And since it has no zeros, there's a well-defined flow. Okay? No two flow lines are coalescing. And so we just follow that flow down, and that flow defines a diffeomorphism. On the other hand, when we cross a critical value, then the topology of these sets XA will change. And so theorem B says that if the interval AB contains exactly one critical value with one critical point, of Morse index lambda, then XA has the homotopy type of what's called attaching an N cell, a lambda cell, to XB. Okay, so now I have to tell you what attaching a lambda cell means. And then what we're going to see is that attaching a lambda cell does not change the homotopy groups ij for j less than lambda minus 1. Okay, so now I have to explain this in detail. Why is that true? Well, we're going to use our Morse lemma here, and let's warm up by considering the simple case where h is equal to minus x1 squared plus x2 squared. Okay. So what are our level sets going to look like? So if epsilon is a positive number, and I write out x sub minus epsilon, it's going to be that set. Whereas x sub plus epsilon is that set. And you see that these spaces are not topologically the same. So here's x sub plus epsilon. Here's x sub minus epsilon. So these are topologically different, right? Because the green region is connected and the red region is disconnected.
But this is just the region of the manifold, so you can't say the entire.
Yeah, but let's take the special. Yes, indeed. Let's take the special case where we're working on, say, R2. But you're right. The Morse lemma only applies to a region of the manifold, but that region, you'll see, suffices. So you see, these are asymptoting to some common place, and so we're not going to get any funny business from there. So the claim is, well, of course, I'm only going to prove these things with pictures like this. You have to look at the books, like Milner's book, for really rigorous proofs. But you can get from this picture to this picture by adding a bridge here. That's going to be, as you'll see in a few minutes, the process of adding a one cell. So putting this in is attaching a one cell. And it has the nice property that it makes the space have the same homotopy type. Now they're both connected, so they have the same pi naught. Okay, so let's upgrade this argument a little bit to n dimensions. Okay, so let's take our height function to be given by locally, given by this Morse lemma, and let's define one radius squared to be x1 squared plus x lambda squared, and the other radius squared to be x lambda plus 1 squared plus x n squared. Okay, and so now let's do the same thing. Let's do the same thing, now projecting to R1, R2 space. So think about this projection for a second. The inverse image of a point here in this projection is a product of spheres. S lambda minus 1 times n minus lambda minus 1. Now, if I go into this axis here, then R1 is shrinking. And so we're shrinking to the origin in this first space. And so along this axis here, we have 0 times Sn minus lambda minus 1. If we go down here, then along this axis, we have S lambda minus 1 times 0. And here, a point is honestly a point. Okay, so let me draw the pictures again. So if we look at x sub minus lambda, then that's this space. And if we look at x plus lambda, that's this space. Okay, and now what I want to do is I want to cut out a region. So we have epsilon here. I'm going to cut out a region like this, with some delta here. And so the blue region here, I'll call C sub epsilon delta. Okay. Now, let's observe that the region this region now here is x sub plus epsilon minus c epsilon delta. This is x minus epsilon. And it's clear that there's a diffeomorphism, a well-defined diffeomorphism, a flow like that, which is well-defined because I'm away from this axis where spheres collapse. So that means that x sub epsilon minus c epsilon delta is diffeomorphic to x minus epsilon. On the other hand, this C epsilon delta is also clearly diffeomorphic to this region here. And this region, so we have a delta here and epsilon here. And this region is just the n-dimensional ball decomposed as the lambda dimensional ball and the n minus lambda dimensional ball. So this shows that we can glue together the n-dimensional ball, thought of this way, to x minus epsilon and get a space diffeomorphic to x plus epsilon. And what do I mean by glue? Well, yeah. So what's the boundary of x epsilon minus c epsilon delta? Well, the boundary is this region here. And what is that region? Well, in the vertical direction, we have dn minus lambda. And then because we're setting R1 equal to a constant, the fiber above there is s lambda minus 1. Now, what's the boundary of the ball here? The boundary, let me write it over here where it's clearer. The boundary of the ball is s lambda minus 1 times dn minus lambda union d lambda times s n minus lambda minus 1. So you see I can glue this to this. And that's the gluing we're doing. So this process is what's known as gluing a lambda handle to a space. So we're taking x, so minus epsilon, times the disjoint union of this, and modding out by an identification where we identify x, y in this space is identified with some f of x, y, where f is a map from s lambda minus 1 times d n minus lambda into x minus epsilon. So this process is called attaching a lambda handle. Now, the disk is contractible, so if you're just worried about topology, the homotopy type, and not the diffeomorphism type, we can contract dn minus lambda to a point and attach a lambda cell. So let me now talk about that. Okay, so let me be a little more precise about the definition. I haven't quite spelled out yet. Dn, of course, is the space of x such that x squared is less than or equal to 1. And that's called an closed n cell. And the interior of Dn is the open n cell. And convention takes us, dictates that the interior of D0 is a point. It's just a convention. Now, if f is a map from sk minus 1 to x, then attaching a K cell to x means you form the following space. X union sub f d sub k, which is x disjoint union d sub k, modulo the equivalence, where we identify x in the boundary of d sub k, that's the k minus 1 sphere, is identified with f of x in x. And f is called the attaching map. And the picture you should have in mind is this. Here's x. Here's the cell, d sub k. And you're gluing the boundary of d sub k, some sphere, into x. So, in terms of homotopy type, I've just justified what I said here in theorem B, that if the critical level goes through a critical point of Morse index lambda, then the level set XA changes its topology by this process of attaching a lambda cell. Are there any questions? So I want to give you a few examples of attaching of cells so you get some feeling for that, and then say one or two properties about it.
So you have a function from a sphere to x, and then this function tells you how to glue to this space, right?
Yeah. So yeah, let's look at a couple of examples. So an example, and here's the simplest possible example. Let's take d sub n. The boundary of d sub n is Sn minus 1. And let's take our attaching map to simply map it to a point. So this is x. That's what you call x sub 0. Then x sub 0 attached by f to d sub n, you recognize as the n-dimensional sphere. You see, you've taken the boundary of this n-dimensional disk, and you scrunch that boundary to a point, and that gives you an n-dimensional sphere. Right? Is there anybody who doesn't find that obvious? All right, so the definition is that given a Hausdorff topological space, X, a CW decomposition is a disjoint decomposition X is the disjoint union of E alpha, where each E alpha is an open cell of dimension n alpha greater than or equal to 0. And 2, let me put 2 over here. To each alpha, there exists a continuous map F alpha from the closed end cell into X, such that restriction to the interior of D of n alpha to E alpha is a homeomorphism. And 3, each point x in E alpha closed minus E alpha belongs to some E beta of strictly smaller dimensions. And if beta is less than n alpha. So when you have a CW decomposition like this, then you can take the union of the various cells, and the xk here is called the K skeleton. The union of all the cells of dimension less than or equal to k. So let's look at a few examples. So I gave one cell decomposition of the n sphere here, where there's one cell in dimension 0 and one cell in dimension n. There's actually a more symmetric cell decomposition. I begin with 2 0 cells. Let's call that D01, disjoint D02. And then I attach a 2 1 cells, D11 and D12. So you see the boundary here is a 0 sphere, and I'm attaching it to the space this way. And then I attach 2 more cells, D12 and D22, so on. So that I have cell decompositions with 2 cells in each dimension. So my cells look like this: xi, 0 in Sn, such that xi is greater than or equal to 0. And then d minus is all this, with xi less than or equal to 0. And so in this way, I build up the sphere with 2 cells in each dimension. Okay. Now, this is a nice, particularly nice cell decomposition because, you see, it's invariant. It's equivariant under the antipodal map. Right, the antipodal map of D plus is D minus. And so, example 2, if we quotient by the antipodal map, then what we see is that RPN has a cell decomposition with 1 cell in each dimension. 0 up to n. Similarly, I'll leave it as an exercise to show that CPN has a cell decomposition. So it's a cell decomposition with 1 cell, 1 0 cell, 1 2 cell, 1 4 cell, up to a 2n dimensional cell. And finally, final example is a Riemann surface we take 1 cell in dimension 0 And then if the Riemann surface is a closed Riemann surface of genus G, we take 2G one cells, and then we take a single two cell, and the attaching map, as it goes around the boundary of this two cell, it traverses this bouquet of circles. Okay. So that's a little more obvious if you do this opening up business. Okay. You think of this interior as the interior of our two-side cell. The boundary of that cell, you see, is joined to these various one cells. And then all of these points here were identified to a single point. Okay, now, so that's cell decompositions. And so now you see one of the beautiful theorems of Morse theory is that every manifold has a CW decomposition. And the proof is by Morse theory. Because that's exactly what our theorem B, unfortunately erased, is telling us. Our theorem B says that as we raise the water level, okay, we get diffeomorphic manifolds if we don't go through critical values, and each time we go through a critical value, we attach a cell. So in this way, we build up the cells. And so, for example, if we went to our torus on the table, we have one cell in dimension 0, two cells in dimension 1, and then one cell in dimension 2. And that's just what I told you you would get for a Riemann surface of genus 1. Okay, now, to complete the picture and understand why Morse theory tells us these facts about the homotopy groups of Grassmannians and unitary groups, we need to know what this attaching does to homotopy. And so the theorem here is that attaching a lambda cell or lambda handle, remember that was, we could always collapse the second disk, does not change homotopy groups for j less than lambda minus 1. So more precisely, we can include pi j into pi j of x union f d lambda, and this is an isomorphism for j less than lambda minus 1, and an epimorphism for j equals lambda minus 1. And let's note that the pi sub j can change, can surely change for j greater than or equal to lambda. And we can see that very clearly from this example right here, where we attached an n cell to a point. So of course the homotopy groups of the point are all trivial. And the homotopy group of the n sphere is not trivial, starting at dimension n. Okay, so what's the proof here? Okay, so the proof is that supposing we have some, not the attaching map, some h, I need a name for a map. Yeah, I see in the notes that that's terrible. Okay. Yeah, so I used F for two things in the notes. F here is some attaching map, but I'm now interested in homotopy, so let's look at some map Q from Sj into X union F d lambda. So what's special about J being less than or equal to lambda minus 1? Well, the important thing here is that since this, here we've attached this lambda dimensional disk, so by homotoping this map Q, we can ensure that the image does not contain some point on the disk. Okay? We can, so the map Q might have some image in this space, but because it's from a space which is strictly lower dimensional than lambda, it has to miss a point. Now, therefore, we can homotop d lambda minus this point n to the lambda minus 1 sphere. So you see we can sort of pull it off the disk. And so that shows that, therefore, any map of a sphere into X union d lambda, where the sphere is of this dimension, can be homotoped to some Q tilde from Sj to X by that retraction. Let me not try and fill in all the details here because I see time is not being kind to me. Now, that shows that it's onto. Therefore, this inclusion, let's call it I lower sharp. Therefore, I lower sharp is onto for j less than lambda minus s and or equal to lambda minus 1. Now, suppose, now we want to show that it's also into when j is less than lambda minus 1. So supposing we have Q1 and Q2, which are homotopic in this attached space. Okay. So that means that there's a homotopy F from Sj times the interval into this space. But again, you see, if j is less than lambda minus 1, then this dimension here, this is dimension j plus 1. So then j plus 1 is less than dimension lambda. So the image of this whole homotopy misses this point. So I can retract the homotopy. And therefore I can determine a homotopy between Q1 tilde and Q2 tilde. And that implies that this map I lower sharp is injective. Okay. So now you can put all this together. We had a Morse function, okay, on the space on the loop space of the unitary group. It had these critical values. Its lowest critical manifold was a Grassmannian. Its next critical manifold had on the order of n unstable modes, Morse index n. Okay? It had Morse index n, and therefore, when we add, you see, it's diffeomorphic up to that next stationary level with Morse index n, and the topology changes for sure when we go through that next level. So our, say too much of this in words. Okay, so our path space of our unitary group, or special unitary group, which was homotopic, our loop space on the special unitary group is homotopic to our path space. And what we see is that that's some Grassmannian union some d lambda 1 with some attaching map F1 union d lambda 2 with some attaching map union, and so on. It's infinite dimensional. And this was the Grassmannian n comma n of C. Okay? And this lambda was greater than or equal to 2n plus 2. Lambda 2 was bigger than that, and so on. So the topology changes here, but it only alters the homotopy groups starting at n. So now, for large n, which is what we're interested in when we stabilize, we don't change the lower homotopy groups, and so that's how the argument goes. Okay. Now, while I'm here discussing CW decompositions, let me make just a few further digressive remarks before we return to Bott periodicity, since CW decompositions are very beautiful in their own right. So there's lots of topology that becomes quite transparent when you have a CW decomposition. That's why, for example, these CW decompositions of the sphere and RPN and CPN are quite useful. So let's notice in general that if we have a CW decomposition, so as I said, we have 0 cells, and 1 cells, 2 cells, and so on. And so imagine that you take the n skeleton and you scrunch the whole n minus 1 skeleton to a single point. Then what you're going to get is the one-point union of a bunch of n-dimensional spheres. So think of the Riemann surface example. If we, already you see it here. If I look at the one skeleton, I have a bouquet of one circles. So that's the kind of picture you should have in mind. Okay, so we have one of these for each n cell n of alpha, n cell E alpha. Now, suppose that n of alpha is n plus 1 and n of beta is n. And let's consider f sub alpha, which takes d alpha n plus 1 into the n plus 1 skeleton. We can restrict this f sub alpha to the boundary of d alpha n plus 1. That's the n sphere. We can call it the alpha n sphere. That maps into the n skeleton. That I can then just collapse the n minus 1 skeleton, which is the disjoint union of n spheres. And then I can project onto the beta sphere. So this gives me a map, let me call it F alpha beta, from the n sphere to the n sphere. And we know that up to homotopy, such maps are classified by their degree. So we get an integer. So we get n alpha beta is by definition the degree of this map, f alpha beta. And so these integers give us the combinatorial data for how these spaces are glued up together. It's really all coming just from maps of spheres to spheres and knowing these integers and alpha beta. And the key point is that if I sum over beta n alpha beta n beta gamma, I get 0. So I'm not going to try and prove that here. So these are n plus 1 cells. The beta, these are n cells. And the gamma are n minus 1 cells. But because of this fact, I can then define something called cellular homology. So the chain group would be equal to the sum of all expressions over alpha of some x alpha e alpha, where x alphas live in some abelian group, G, and I sum over k cells. And now the boundary map on E alpha is the sum over beta of n alpha beta E beta. And then because of this identity here, the boundary map squares to 0. And so therefore I have a chain complex. So I have ck to ck minus 1, ck minus 2. So I then have a complex. And so then, as usual, I can take the homology of that complex. And the theorem is that the homology of this chain complex with respect to delta is one way of defining the homology of x with coefficients in an abelian group G. So I felt kind of bad that I hadn't covered cohomology and homology for you guys. But then I realized, well, okay, as long as I'm doing CW complexes, I can give you that as a definition of homology. And, well, so let's, as an application, calculate the Euler character. In fact, let's do a little better than the Euler character. Let's calculate the homology of the n sphere. Well, you see, with coefficients in z. Well, you see, from our presentation in terms of x0 and dn, it's clear that it's z for star equals 0, 0 for z for star equals n, and 0 otherwise. Similarly, let's calculate the homology of CPN. See? Okay, the homology of CPN is easy, you see, because it has this beautiful property that all the cells are even dimensional. So that means that since the boundary map goes from cells to cells one dimension lower, it must be 0. So that means that the calculation of the homology is completely trivial. It's equal to z for star equals 0 to 4 up to n, and 0 otherwise. Now that won't work for RPN. So maybe as an exercise, in fact this is a great exercise. homology, that H sub j of Rpn, the coefficients in Z, is Z for j equals 0, Z2, j equals 1, 3, 0 for j equals 0, 2, 4, and Z, or 0 for j equals n, depending on whether n is even or odd. So that's the best way to say this. Z, if j equals n is odd, 0 if j equals n is even. These numbers are less than n, and 0 otherwise. And so you can get that right out of the cell decomposition of RPN. All right, let me finish this digression on Morse theory by just mentioning briefly the relation to supersymmetric quantum mechanics. So from the physical point of view, one nice approach to Morse theory was discovered in a really brilliant paper by Edward Witt around 1982 or so, where he considered supersymmetric quantum mechanics and so we have a bosonic particle from the real line or the interval into our Riemannian manifold X. And then I remind you that long, long ago, we noted that T sub phi of the mapping space of, in fact, any S into X is isomorphic to the sections of the pullback of the tangent space of X. Now, supersymmetry variations are going to define tangent vectors to the space of maps. And so our tangent vectors, if we choose local coordinates, so we write phi mu of time, our tangent vectors are going to be some kind of psi mu of time. And if I take n equals 1 supersymmetry, they'll have canonical conjugates, psi bar mu, and these will satisfy the canonical commutation relations, which is given by Clifford algebra. Now, we can quantize that Clifford algebra. It's a real Clifford algebra. So we can quantize that by identifying the Hilbert space of this theory with the de Rham complex of X. So psi mu is then wedge with dx mu and psi bar mu, psi bar lower mu, yeah, I should probably do it that way, is contraction with d by dx mu. And so a superfield, if you were doing supersymmetric quantum mechanics, you would have a wave function, which would be some function of phi and psi, and you would expand that in fermions. Put a 1 over k factorial here with some coefficient functions, which are functions of bosons. And you see that with this identification, these wave functions are canonically associated with differential forms. So the Hilbert space, then, is canonically the de Rham space. And now superpotential, okay, which is a real valued function from x to r. Does that sound familiar? A real valued function from x to r. That's going to be our Morse function, of course. With a superpotential, the supersymmetry operators are Q equals I times e to the minus w d e to the w, and Q dagger, which is I e to the minus e to the plus w, d dagger e to the minus w. So you see Q squares to 0, the Q dagger squares to 0, and the Hamiltonian, which is the commutator of Q with Q dagger, is first of all what's called the Hodge Laplacian. But then we get the gradient of W squared, and we get fermionic terms, sine mu, psi bar nu, d squared W by d phi mu, d phi nu. Okay, so if I have a Morse, okay, so now Witten had a very clever idea, which was if you have this W, you in fact have a whole family of supersymmetric theories where you scale W by some real number s, and we have s squared here and s here. And now we studied the case where s goes to infinity. And we're looking at supersymmetric states. Which, of course, are annihilated by Q and Q dagger. A different sign. I guess I used capital sign. So supersymmetric states would be annihilated by that Q and Q dagger. Okay. That's what unbroken supersymmetry means. See, Witten was interested in a hierarchy problem, and so he was interested in supersymmetry solving the hierarchy problem, so he was very interested in the question of whether whether you could study perturbative supersymmetry breaking and how that was changed by non-perturbative supersymmetry breaking. So he started playing around with supersymmetric quantum mechanics, which was quite a brilliant thing to do. So the supersymmetric states are this. Now, at s equals 0, they are the harmonic forms. Okay. So the number, and we can give these size a fermion number, so the number of forms with fermion number k is the number of k forms, harmonic k forms, and that's the Betty number. That's another way of thinking about cohomology. But you see, you can conjugate by this W, and if W is a well-defined function on the manifold, then you can, as W, you can also look at this. There have to be the same number of supersymmetric states as s goes to infinity. But in that approximation, these terms are going to dominate the energy. So the perturbative supersymmetric states are in one-to-one correspondence with the Morse critical point, with the critical points dW equals 0. And if they're Morse critical points, then the fermions have non-degenerate masses. So now you can understand the Morse inequalities. You see, what's going to happen is there are going to be, more, in general, more critical points than are required by topology. Okay, but then they're going to be instantons lift perturbative supersymmetric states. So there are more perturbative supersymmetric states than there are non-perturbative exact supersymmetric states. And that's essentially the Morse inequalities. We could do that in more detail, but time's running out. Moreover, we have these flows which are given by the instantons. Well, these flows, you see, define this kind of CW decomposition. And this kind of cellular homology that, so Witten wrote down a homology complex who's generated by the critical points. And this is another complex, very much like the cellular homology complex, for calculating the homology of the manifold. So that paper led to a lot of work, and indeed a whole subject in mathematics, which is still a very intensely studied subject in mathematics, called floor theory. Okay, so I've gone about twice as slow as I expected to do. So next time, which is Monday, next week is funny, being Thanksgiving week, but we do have class on Monday. And next time, the first thing I'm going to do is I want to finish talking about Bott periodicity. So the main thing I want to say there is we have this periodicity theorem. Now we've talked about the unitary case. I want to say a few words about the orthogonal case, right? It's got to be more complicated. You have the whole mod 8 periodicity. How does that work? I'll say a few words, but I won't go too deeply into that. But what I do want to also point out is a beautiful relationship to Clifford algebras. So if you know anything about Clifford algebras, you know that, certainly those of you who took my group theory course last year should know, that the complex Clifford algebras have a mod 2 kind of periodicity, and the real Clifford algebras have a mod 8 kind of periodicity. And that's very deeply related to Bott periodicity, so I'll just say a few words about that. And then we're off on to vector bundles.